Swayam Prabha. Digital India. Educated India.
Good morning to everybody. Today we will discuss about two-dimensional heat conduction problem, and we'll discuss about an analytical solution. Let us consider a plate which has a dimension L in the x direction and W in the y direction. Temperature on three sides, left side, bottom side and right side, temperatures are T1, and on the top side temperature is T2, and T1 is different than T2. It is quite obvious. Therefore, we now define a non-dimensional temperature which is T minus T1 divided by T2 minus T1, so that anywhere on the plate temperature varies between 0 and 1. Now, and we have formally written the boundary conditions. Theta 0 y, all along y at x equal to 0 is 0. Theta at Ly is 0. Theta at x0, the bottom side, is 0. And theta at xw at the top is 1. So these are the domain of the boundary conditions. Theta 0 between y0 and w, theta Ly 0 between yl and w, theta x naught equal to 0 between x, 0 and l, theta xw equal to 1 between x, 0 and l. So left hand side 0, bottom side 0, right hand side 0, top side 1. That is the non-dimensional condition. Otherwise, dimensionally, left side T1, bottom side T1, right hand side T1 and top side T2. Now, and L is the length of the plate, W is the width of the plate. So, on this domain, we can assume existence of a solution which is given by theta equal to uppercase X, which is function of X, and uppercase Y, which is function of Y. So basically, theta can be thought of product of these two functions, which are also indicative of temperatures. So separation of variables we will apply. Basically, in this technique, solution is the product of two functions, x, which is function of x, uppercase X, which is function of X, uppercase Y, which is function of Y, and product of these two functions will give theta. Product of uppercase X and Y will define final distribution of theta. And here, so basically governing equation is Laplace's equation del 2 theta del x2 plus del 2 theta del y2. Two-dimensional problem. So in dimensional form, del 2t del x2 plus del 2t del y2 equal to 0 is indicative of temperature distribution on a domain. And if we non-dimensionalize it, non-dimensional form, we can write del 2 theta del x2 plus del 2 theta del y2 equal to 0. And theta is given by uppercase x into uppercase y. So we perform double derivative of theta with respect to x. That means it will be x double prime, and also theta with respect to y, which will be y double prime, divided by theta, and we get this expression. And then we separate out the variables. Obviously from here we can write x double prime by x equal to y double prime by y, or minus x double prime by x, that is 1 by x d2x dx2 equal to 1 by y double prime. So 1 by y del 2y del y2. So we separate them out and fix a separation constant lambda square. The usual separation of variable steps or techniques involving separation of variable we have applied systematically step by step, and we have reached this condition or reached this state where minus 1 by uppercase x into d2x dx2 equal to 1 by uppercase y into d2 uppercase y dy2 equal to lambda square. Lambda is the separation constant. So we can equate basically this x derivative equal to lambda square and the part which is y derivative equal to lambda square. So exactly we have done that. d2 uppercase x dx2 plus lambda square uppercase x equal to 0, and d2 uppercase y dy square minus lambda square uppercase y equal to 0. Now solution of this part is given by c1 cos lambda x plus c2 sin lambda x, and solution of this part is given by y equal to c3 e power minus lambda y plus c4 e power plus lambda y. Then we can, as we said, the final solution is product of these two solutions, uppercase x into uppercase y. So we can write c1 cos lambda x plus c2 sin lambda x into c3 e to the power minus lambda y plus c4 e to the power plus lambda y. So this becomes the expression for theta. Boundary condition 1, if we recall, which was at x equal to 0, that means theta at x equal to 0, and throughout y, that means y is between 0 and w equal to 0. This is on the left hand side. This boundary condition physically obtainable, and we apply that. If we apply that, that means we have to substitute x equal to 0 in this expression. We will get C1 C3 e to the power minus lambda y plus C4 e to the power lambda y equal to 0. And this gives us the obvious outcome or obvious choice that C1 has to, if this has to be 0, C1 must be 0. Now if C1 is 0, then again we can go back to the solution. We can write theta equal to C2 sine lambda x into C3 e to the power minus lambda y plus C4 e to the power plus lambda y. We have to find out all these constants, no? C1, C2, C3, C4. So C1 we have found as 0, and now theta can be written as this. Now, since theta is C2 sine lambda x into multiplied by C3 e to the power minus lambda y plus C4 e to the power lambda y, on this we write boundary condition 3. That means at the bottom of the plate where y equal to 0. So theta throughout x is between 0 and L throughout the length of x, and y equal to 0 equal to 0. Now if we have to substitute this in this equation at y equal to 0, we will get C2 sine lambda x, and y equal to 0 and y equal to 0 we have substituted C3 plus C4 equal to 0. Now in this equation, if C2 equal to 0, then we will eliminate x dependent part of the solution altogether, because C1 is 0. If C2 is 0, then there will be no dependence on x. So this is unacceptable. So that means this bracketed terms together are 0. So C3 plus C4 equal to 0. That means we can write C3 equal to minus C4. And then if we substitute C3 equal to minus C4 in this expression for theta, we can write theta equal to C2 sine lambda x into C4. We have substituted C3 equal to C4 and taken it outside the bracket. Inside the bracket we can write minus e to the power minus lambda y plus e to the power lambda y. So this becomes the expression for theta, basically C2 C4 into sine of lambda x multiplied by e to the power lambda y minus e to the power minus lambda y. And in this, now we apply boundary condition on the right hand side, boundary condition which is available on the right hand side. That means boundary condition 2, at x equal to L, theta L throughout y, where y is between 0 and W, theta Ly is 0. So here if we substitute x equal to L, we can write C2 C4 sine lambda L into minus e to the power minus lambda y plus e to the power lambda y equal to 0. After substituting this, we can write this. Here again we'll see the only way this can be reached if we apply a special condition on sine lambda L, because C2, C4 we cannot make that equal to 0. So sine lambda L equal to 0 for specific values of lambda. One way in which this condition may be satisfied is by requiring that lambda assumes discrete values for which sine lambda x equal to 0. These values then must have the form lambda equal to n pi by L, because lambda has to be 0, lambda has to be such that sine lambda L is 0. So that will be satisfied. Those lambda values have to be found out for which sine lambda L is 0. So lambda then will be given by n pi by L, where n equal to 1, 2, 3 or any integer. Lambda equal to pi by L, lambda equal to 2 pi by L, lambda equal to 3 pi by L. For all this, sine lambda L equal to 0 will be satisfied. So we can write theta equal to C2, C4 sine, just I am going back by one slide, in this expression C1, C2, then sine n pi x by L into e to the power lambda y minus e to the power minus lambda y. So theta equal to C2, C4 sine n pi x by L into minus e to the power minus lambda y plus e to the power lambda y. Now you can see n equal to 0 also satisfies this condition, but we will exclude, because then theta will be independent of y. It will always, we have to substitute 0, lambda equal to, if n equal to 0, lambda equal to 0, we will get rid of this part. So lambda n equal to 0 is not included, as I said, because then theta will be independent of y. Y dependence will be gone. So we will exclude n equal to 0. We will write n equal to 1, 2, 3, any integer. So theta is given by, then we can write n equal to 1, 2, 3 up to infinity, the series, any integer, Cn, C2, C4, etc. they are clubbed into Cn, and then sine n pi x by L into sine hyperbolic, because this part will be sine hyperbolic n pi y by L. Okay, so we can this will be e to the power lambda y minus e to the power minus lambda y by 2, which is sine hyperbolic lambda y, and lambda is n pi by L. So this part is sine hyperbolic n pi y by L. So this is the complete solution, but in this solution still one unknown is there, which is Cn. In order to determine Cn, we apply fourth boundary condition, which is at y equal to w, that is on the top surface, theta throughout x at y equal to w is 1, and x extent is between 0 and L. So theta xw is 1. Now we apply this condition here, and that means we will get y equal to W we have to substitute. So in this summation, n equal to 1, 2, 3 up to n, Cn sine n pi x by L sine hyperbolic n pi W by L equal to 0. And n pi x by L is lambda nx. That we have seen earlier. We are calling n pi by L as lambda n. Now, at this juncture, we have to apply the properties of orthogonal function. What we have to do in the domain limit between 0 to L, we have to integrate this with respect to delta x after multiplying with sine lambda mx. And right hand side also we do the same. We integrate between 0 to L sine lambda mx dx. This is the basically property of orthogonal function that we are making use of. So from here we can write summation n equal to 1, 2, 3 up to infinity, any integer, Cn sine hyperbolic lambda nw, this part equal to, we can write 0 to L sine lambda nx divided by 0 to L again sine square lambda nx. Here we have generalized n and m in such a way that, see, this is n or m are same, and this part is basically integration of sine lambda nx into sine lambda mx. If we say m equal to n, then we can write sine square lambda nx dx, and so this integral divided by, if we pull out sine lambda nx, multiply it with sine lambda mx, which is again equal to sine lambda nx, how I can explain it little later, dx. So this part can be written as an. So this series, which is n equal to 1, 2, 3 up to infinity, Cn sine lambda n into w, we can write as sine hyperbolic lambda n into w, sine hyperbolic lambda n w, this equal to an. And while evaluating this an, we have to make use, because this integral which we have written as 0 to L sine square lambda nx dx, this is actually 0 to lambda sine lambda nx into sine lambda mx dx. When m equal to n, then we can write sine square lambda n x dx. And this, how we can write, again this is property of orthogonal function. Between between a and b, if we integrate sine lambda nx sine lambda mx dx, this will be 0 for n not equal to m, and this will be non-zero only when n equal to m. So sine lambda x into sine lambda nx into sine lambda mx dx. When m equal to n, then it is sine square lambda nx dx. And then only it will be non-zero. Otherwise, it will produce 0. For n equal to m, this will be sine square lambda n x dx. And integral of sine lambda nx dx divided by integral 0 to L sine square lambda nx dx, which is an, it is given by 2 by n pi into minus 1 to the power n plus 1 plus 1. How? We will show in the next slide. Just integration of this divided by integration of the denominator. That is an, and value of an is 2 by n pi multiplied by minus 1 to the power n plus 1 plus 1. And how this part can be performed, we'll show in the next slide. 0 to L sine n pi x by L dx. We can write this integration is minus cos n pi x by L into L by n pi, limit L to 0. And if we substitute the limits, we will get L by n pi into 1 minus cos n pi, which can be written as L by n pi into 1 plus minus 1 to the power n plus 1, the value of cos n pi. Now 0 to L sine square lambda nx dx, this we can write basically sine square theta equal to half 1 minus cos 2 theta, that trigonometrical identity we use. So half 1 minus cos twice lambda nx dx. If we perform the integral, half x minus 1 by twice lambda n sine twice lambda nx, and we have to substitute this upper limit and lower limit. Having substituted this upper limit and lower limit on x minus L by twice n pi sine twice pi x divided by L, we get L by 2. Now this quantity was the numerator, this quantity was the denominator, and we from here, if we divide this by L by 2, we'll get an equal to 2 by n pi into minus 1 to the power n plus 1 plus 1. So that is what we'll go by one slide. That is what was our target, to show that this an is given by 2 divided by n pi into minus 1 to the power n plus 1 plus 1. So this, if we can find out this, then we can evaluate Cn. So an we have shown how it is obtained, and then we can write Cn n equal to 1, 2, 3 up to infinity equal to then twice pi into again the summation over n equal to 1, 2, 3. So an we have written as minus 1 n plus 1 plus 1 by n. So that is what exactly we had to write, and pi, 2 by pi we have taken out, 2 by pi we have taken out, this divided by n, the numerator divided by n, and this is exactly we have written. And then here with Cn we had sine hyperbolic lambda nw, this will go to the right hand side. So sine hyperbolic lambda n w by L. So this is the value of Cn. So before evaluating the value of Cn, theta, we reached up to this stage, that's theta is given by summation over a series where summation is done for n equal to 1, 2, 3, etc. up to infinity. Cn sine n pi x by L into sine hyperbolic n pi y by L. And Cn value, we have found out this. Now we can write theta xy equal to 2 by pi, this series we can bring in 2 by pi into summation minus 1 to the power n plus 1 by n sine, this is the value of Cn up to this, then sine n pi x by L and sine hyperbolic n pi y by L, and we had in denominator sine hyperbolic n pi w by L. So this becomes a complete analytical solution that will give us distribution of temperature anywhere on the plate. We have to substitute the correct value of x and y, and depending on x and y coordinate, we can get exact value of theta anywhere on the plate. That is the beauty of analytical solution. Now we'll take up an example where we will find out temperature at a specified location in the domain, or any given location in the domain. We'll specify where we want. So this is a plate which is basically, we can see that 0.6 meter long and width is 0.4 meter, and we have to find out temperature at a location x equal to 0.3 meter and y equal to 0.2 meter. Or in other words, this is a plate, and this plate is having dimension 600 millimeter in the x direction, its length is 600 millimeter. In y direction, its dimension is 400 millimeter. And we have to find out temperature at x equal to 300 millimeter and y equal to 200 millimeter at a location P, which is location wise at 300 millimeter, its x location, and y location is at 200 millimeter. So, and on 3 different sides, temperatures are 100 degree, and top side of the plate temperature is 400 degree. That means the problem that we have solved, according to that problem, T1 is 100 degree and T2 is 400 degree. So if we go back by our solution, which was given by xy equal to this basically summation over this series, where n equal to n can be varied from 1 to 3 up to infinity, we can take n equal to 1 and 3, and that will give us accurate enough solution. So we can write t minus t1 divided by t2 minus t1, that is theta, equal to, now we can substitute n equal to 1, find out the expression, n equal to 3, find out the expression, and then we will see for n equal to 1 sine within bracket sin xp by L sin hyperbolic sin pi xp by L sin hyperbolic pi yp by L divided by sin hyperbolic pi w by L plus sin 3 pi xp by L into sin hyperbolic 3 pi yp by L divided by 3 sin hyperbolic 3 pi w by L. And then that means that every quantity has to be evaluated, which we have done. Sin pi xp by L, which is sin pi by 2 equal to 1. Sin pi yp by L, sin hyperbolic pi yp by L equal to sin hyperbolic pi by 3, which is equal to 1.25. Sin pi w by L, which is 0.866. Sin hyperbolic 2 pi by 3, which is 4. This way, all these quantities, sin pi xp by L, sin hyperbolic pi yp by L, sin hyperbolic pi w by L, all these quantities are evaluated and substituted, and we can see Tp minus 100, 400 minus 300, T2 is 400, T1 is 100, Tp minus 100, 400 minus 100 equal to 4 by pi into, just it's matter of algebra, 0.3125 minus 0.144. So finally Tp is 213.85 degree centigrade. So that's what was our aim, that we will analytically find out an expression, so that in that expression, if we substitute correct value of the x and y coordinate within the domain of any location, we will be able to find out temperature of that location. Now, in this evaluation or analytical technique, we used basically properties of orthogonal functions. So let me give a very brief overview about the properties of orthogonal functions. An infinite set of functions like g1x, g2x up to gnx is said to be orthogonal in the domain, and where the domain is between greater than equal to a, less than equal to b. This infinite set of functions are orthogonal if we can write between a and b gmx into gnx dx equal to 0. And this will be for m not equal to n. Many functions exhibit orthogonality, including the trigonometric functions sin n pi x by L and cos n pi x by L for x greater than 0 and less than L. Their utility in the present problem rests with the fact that any function fx may be expressed in terms of an infinite series of orthogonal functions if fx is given by n summation n equal to 1 to infinity an gnx summation over an gnx, where n equal to 1, 2, 3 up to infinity. The form an in the series may be determined by multiplying each side of the equation by gnx and integrating between a and b. So this fx, if we integrate between a and b, by multiplying gnx, and right hand side also we do the same, between a and b, fx gnx dx, a and b gnx multiplied by this series a n gn n equal to 1 to infinity dx. However, from this property, where we have written m not equal to n means this integral is 0. So from 1 it is evident that all but one of the terms on the right hand side of equation 3 must be 0, leaving us with, so when m not equal to n, this will be 0, leaving us with 0 to b fx gnx dx equal to an gn square x dx. So this m, or we can read this an gmx dx is being multiplied by gnx, and when gmx is gnx, then only it makes sense, it is non-zero, otherwise it will be 0. So from here we can write an equal to a to b fx gnx dx divided by a to b gn square x dx. So this property we used here in this typical analytical solution to find out the value of Cn. If you recall, we found out the value of Cn by deploying the properties of orthogonal functions. We'll stop here today. Thank you very much. Thank you for your interest.